In this video, we're talking about regression in machine learning. This is the first part in a series of videos dedicated to this topic. As we know, the supervised learning is divided onto two main categories, regression and classification. Regression pertains to the prediction of continuous variable, and classification concerns prediction of discrete variable. And so, as usual, we have some training set, which implies we're having some features x and corresponding labels y. And then we can apply some learning algorithm, which will allow us some classification rule or function f, which will help us to map the features to corresponding predictions y or y hat, as is shown on this slide. In this video, we are considering just a univariate regression. It means that prediction of variable y based on the values of one-dimensional variable x. So, for example, we are having such amount of data, y dependent on x, and the goal of linear regression is to find the average linear dependence of variable y based on the values of variable x. And so we want to find the equation of the line with the weight coefficient w and bias b. Okay, so as we know, this weight coefficient w corresponds to the tangent of angle, which is formed by the line with the x-axis. We can show this also in using this small Python script. Okay, we have the same set of pairs x and y, and we can see how the line which we are trying to construct, which approximates these data points, depends on the value of w of b. Now I'm changing the bias b, and now the change of w, which like a magic wand slides here on this graph. So we're interested in finding some optimal values of w and b, which correspond in some optimal way of our data. Let us consider a specific example. This is a so-called car small data set. It consists of data for different cars containing their weight, horsepower, acceleration, and consumption, which is expressed as miles per gallon. And I will show it in Colab, the corresponding script. Yes, we are loading our data. Here we use a pandas component to represent the data about 93 cars, and we can plot them. We can plot the corresponding data on the graph x and y. So, and we may be interested in constructing some line. Yes, for each line that we construct, which tries to approximate this data, we will have a corresponding error. Mean square error, which is here denoted as MSE, and RMS usually is for the square root of MSE. So this is another kind of traditional expression for the value of error. And for example, here I'm just choosing 2 points, and I'm building a line which connect these 2 points and see how it can approximate our data points. For example, here I took 6 and 12 points in our data, or I may take, for example, 6 and 15. We have another value of error, and so let us go further. What is our next question? For example, here we consider the dependence of y is miles per gallon, the consumption parameter, and x is the weight of the car. And we're interested on optimal prediction of miles per gallon consumption based on the weight of the car. Yes, as we have seen now in Colab, we can choose different combinations of W and B, and it will provide different lines with corresponding errors. But the question is how to find the optimal approximation. How can we find optimal parameters W and B to provide the minimum error? Of course, to apply some learning algorithm, we must have training data, the labels Y, and we must set the optimality criterion. The most popular cost function is shown here on the upper part of the slide. This is a mean square error, as we usually understand it. Usually, maybe it is also traditionally divided by the number of elements, normalized mean square error. And if we take this criterion as base, we can see that our cost function, this expression, the total error for different data points, this is called cost function. And this cost function, in this case, happens to be convex. Convex, it means that it has a strictly present, well displayed local minimum. Local minimum, which also is a global minimum. We can run the corresponding script in Colab, and we are building this function which looks like a cup. Yes, which looks like some kind of a cup or a hand. Yes, we see that this surface has some minimum point. How can we find this minimum point? Yes, also one important point which I didn't mention, that feature scaling, where we to build this surface, we had to scale our features, scale data X, because without data scaling, this surface for the cost function would not be so distinct. If I am canceling the data normalization, yes, I will see what I will show what's the difference. The cost function will look in another way. Yes, such way. It is still convex. But it's much more difficult to find a point of local minimum. That is why the normalization is essential. Normalization of data is essential. The most usual way of normalization is by subtracting a mean value of our array X and divided it by standard deviation of this array, which is performed by the shown 2 lines of Python code. So again, no scaling and scaling. Even at the very beginning of linear regression, we are facing the problem of scaling. We need to scale the data so that X and Y will be approximately of the same scale. So I will return the scaling, which we found to be essential here. I will run again, and we will have our convex surface, which again looks like a cup. Okay, so let's go further. And having this cost function in a univariate case, we can find the optimal values of W and B by computing gradient of our cost function. By taking the partial derivatives of cost function by W and B and equating them to 0, we can get equations for the optimal W and B. I will show how they are here. They are represented by these formulas, W0 and B0. We can calculate these values and show I'm not sure this is an optimal line. No, there should be W0 and B0. Yes, and here I will replace it by okay, it should be so. Yes, this is the optimum line. This is the optimal line. We can see the corresponding mean square error and RMS, root mean square. Okay, and the question, of course, is it possible always to find this solution, optimal solution, by such closed form formulas? But unfortunately, no, this is possible only in linear case and in general with a relatively low number of variables. In univariate case, yes, it's possible, and we have the following formulas. But it can be, as we will see further in the next video, it's not so convenient to generalize for the large number of variables. We will have so-called normal equation, which is not convenient to solve when we have a lot of variables. So we will talk about the very popular solution for this kind of problems, which is called the gradient descent. Gradient descent is based on the fact that the gradient or a vector of partial derivatives of some function, in our case the cost function, gradient shows the direction of the steepest ascent of the function. And correspondingly, when we're interested in the finding of local minimum of the function, anti-gradient, that is the gradient with the inverse sign minus gradient shows the direction of the steepest descent of the function. So we must move across our function, across our surface on the left or on the right in the direction of anti-gradient, and by regulating also the step with which we with which we descend. This step should be taken so that we are always moving below. We're decreasing the value of cost function at every step. So we will see how it can be expressed by the formulas. Suppose we have some parameter theta, and in our case, it could be either W or B, weight coefficient W or bias B, and we're decreasing it by some weight coefficient alpha, which is called learning rate, multiplied by the gradient of cost function, corresponding cost function. So what does it mean in our case? We have already seen that on the left how to calculate the gradient of cost function, and it means just the update equations for the W and B are of the following form, as shown on the right. So having these formulas, we can apply the gradient descent method. Of course, it is essential to find appropriate learning rate alpha. If alpha is too small, the gradient descent converges very slowly. Otherwise, if alpha is too large, then the gradient descent may never reach minimum. It could be fail to converge. It can diverge, in fact. So this is the general strategy of gradient descent method. It means that we have our cost function. We want to find its minimum. We start with some initial approximation of W and B, and we are changing them according to the equations of gradient descent method until we reach the minimum point by some criterion, by some rule. We understand that we are near the optimum, we are near the local minimum. Yes, of course, in general case, but not in this case. In general case, there could be multiple local minimum. But in our square error cost function for linear regression, there is only one point of local minimum. Okay, if we return to our car-small data set, we can see this example how gradient descent method converged to the point of local minimum. It is depicted both directly for the surface of cost function, which is shown on the left, and on the right for the contour plot of this cost function. So these points correspond to different iterations of gradient descent method. And here we see the influence of learning rate. These are the influence of learning rate. If we take a very small value of learning rate, the algorithm of gradient descent converges very slowly. It may converge fast if we take a large value of learning rate, 0.5 in this case. But we should be very careful. I can show you that if we if we select unnecessarily high value of learning rate, I will run the gradient descent now with the low learning rate. Yes, it decreases very slowly. Now I will take some value higher, 0.1. So it converges quickly, quite quickly. Yes, we are having the stable value of cost function, minimum value of cost function. But if I am increasing even more, for example, 0.5, I'm taking this learning rate. Yes, it still converges. Let it take 1, for example. Still converges. Okay, let us take equal to 10. Gradient descent. Yes, now it diverges. Yes, we have fantastically high, very large numbers of cost function, and it diverges. So we must be very careful with the selection of proper learning rate. One additional detail which I wanted to point also here, that we can optimize the computational implementation of gradient descent method by using vectorizing. So I have here source code for the gradient descent as we discussed it just now. Yes, this is the update of W and B, and it means that for at each iteration of gradient descent method, for all our data points, we have to accumulate the gradients of W and B, and also accumulate the cost function. So it should be done at every iteration. We must go across the whole data set. Yes, it can be simplified from the computational point of view, from the identical version, if we use the vectorized algorithm. I will show, yes, where we use the possibilities of Python or MATLAB or many other computational platforms. They are highly effective when using vector computations. Just by one line, we can compute, for example, the cost function for the whole data set. There is no need to consider separately different data points. Yes, it can be done at once. For a particular iteration, we can compute the gradient by W and gradient by B just by one line, by using the vector possibilities of corresponding computational platform. And I will also show for example, the comparison of time. Yes, if the scalar gradient descent implementation took 0.9 seconds for the five runs of this algorithm, then 9 times lower time took the implementation of vectorized gradient descent. So we also must take it into account when writing our programs to implement the gradient descent method. So I think that's all what I wanted to say in this video about the linear regression. We considered univariate linear regression. And in the next video, we will show how can we implement the multivariate linear regression, and also how to deal with the multivariate linear regression. Thank you very much for your kind attention.